We looked at a really simplistic model of growth and decay yesterday, so we're going to expand on that idea a little bit. So we're going to take into account some other conditions that may occur. The classic one is the law of cooling. So the example there is that the temperature of an object can never be lower than the temperature of the surroundings. Okay, so if you're taking it out of an oven, I should say, if you're taking it out of a fridge, then it could never get higher than the temperature of the surroundings. So we need to change our equation to take that into account. And it's a simple little fix. Instead of saying that our rate of change is proportional to the population itself, we make an adjustment and we just say P minus N. Now, when we solve this one, we end up with, well, we could have the possibility that P is equal to N. That's what we call the trivial case, if you think about it, because if you differentiate N is just a constant, so if you differentiate N, what do you get? Right, so we're saying that the P to T would be 0. All right, now go back to our derivative. If P is equal to N, the derivative is 0, because you get N minus N. So that's what we call the trivial case, and we don't usually consider that one. The more interesting case is this one. N plus AE to the KT. So we've got the same solution as our basic model, but we've done something to it. We've added N. Now, if you were to imagine the graph of this, what have we done to that graph from yesterday? Yeah. So in effect, because we're talking about an exponential, we've shifted it up or down depending on what N is, but it means our asymptote's changing. Instead of going asymptotic to the axis, it'll go up or down. So that N is the outside influence. Remember I said with the example of a temperature, it'll never go lower than the temperature of its surroundings. So if it was starting at a high temperature, it'll come down, but it'll go asymptotic, not to the axis, it'll go asymptotic to whatever the temperature of the surroundings is. So we just basically shifted the curve up to that point. So P still represents population, but now N plus A would be the initial population. K is still our growth or decay constant, and T, of course, is still time. So it's quite an old question now, but to use that idea of temperature, so T is representing temperature inside the room at time little t, and capital A is that constant air temperature of the outside surroundings. So Newton's laws of cooling, he did many different laws over the years, but the law of cooling actually states that the rate of change will be proportional to T minus A. So similar to yesterday, we don't know how to integrate our exponential functions yet, but the first part then they'll probably ask us at this stage is to just verify the solution, show that it works. So our solution to our equation would be T equals A plus CE to the KT. C and K are both constants. Okay, so there's T. We want to differentiate capital T with respect to little t, and we get KCE to the KT. Now remember, we want it proportional to T minus A. Well, T minus A, if you have a look at the original T equals A plus CE to the KT, if I was to rearrange that, T minus A is CE to the KT. So I could replace that, and there's our solution. We've got some constant times T minus A. So it's directly proportional to T minus A. So yes, that solution does satisfy the equation. So now let's put that into practice. So the outside air temperature, 5 degrees Celsius. So early in the morning. Yeah. The heating system has broken down. So the inside room temperature drops from 20 to 17 in half an hour. So after how many hours will the temperature drop down to 10 degrees is the question. T equals 5 plus CE to the KT. Remember, 5 is where we've risen the asymptote to, the outside air temperature, which we said was 5 degrees. Now, when T equals 0, the temperature is 20, so that means capital C is 15. Again, we said those two constants would add together to give the initial temperature. So we end up with 5 plus 15e to the KT. We now need to work out our growth, or in this case it'll be a decay constant because we're decreasing in temperature. Well, we've been told that half an hour it drops down to 17. So we know when T is 0.5, capital T is 17. So we just need to rearrange this, make K the subject, 15e to 0.5k is 12. Divide both sides by 15. To undo the e, we log both sides. So I've got 0.5k is log of 12 on 15. So my k is twice log 12 on 15. I suppose I could write that as log of 1215 squared if I wanted to bring the 2 in. Doesn't really matter. There's an exact value for k. So now we want to know how long till it drops to 10 degrees. So it's same equation, but this time we want to find little t. Notice I'm carrying through k rather than writing down 2 log and so on. So eventually we get 1 on k log of 1/3, bugging that all into the calculator, 2.46167. The question said after how many hours? I suppose technically 3 hours, but I think I went for 2.5, didn't I? Yeah, I mean 2.46, so close to 2.5. Again, that's what I was saying yesterday. Write down your decimal approximation so they can see where your conclusion has come from, rather than just looking at it and going, oh, I think it's 3 hours, I think it's 2.5 hours. All right, so very similar idea to yesterday. All we've really done is we've raised the asymptote to take into account the external conditions.